Para todos, vamos a dar inicio con el evento. Les invitamos a que por favor pongan sus celulares en silencio para que no tengamos interrupciones. Muchas gracias. This event. So, welcome to the opening of the International Symposium on Science. Director of Research Center, Faculty of Engineering, SEDEC. Dr. Hernán Olaya Dávila, Director of the Physics Program. Dr. Hans Yesid Ramirez, Chairman of the International Symposium on Quantum Science and Engineering, as well as Dr. Paul Haverlach from the University of Ottawa, and all our international guests, professors, young and emerging researchers, students, and university staff. From today until next Friday, you can see with IQSE 2025, International Symposium on Quantum Science and Engineering, an event through which our university joins the celebration of of research group Quantum Computing and Information Theory, IQSE, and Theoretical and Computational Physics. Thank you for turning our university into a hub of scientist interaction and exchange around quantum physics and its applications. The program with which we begin this event is the following. First, Colombian National Anthem. So we invite you to stand up. Thank you. Second, UPTC Anthem. Third, words by Dr. Abraham Augusto Melo Castañeda, ICT Manager, who is representing the Mayor's Office of Tunja.
Good afternoon, everyone. It is a great pleasure to greet you on behalf of Mayor of Tunja, Mikhail Krasnov, and Municipal Administration. We are honored to welcome you to our city to the International Symposium on Quantum Science and Engineering, IQS 2025, here at UPTC. This event brings together 14 distinguished experts from 8 countries, a true reflection of global collaboration and a growing importance of quantum science in shaping the future. This is a privilege for Tunja to host such a remarkable meeting that connects knowledge, innovation, and scientific progress. Our city is deeply committed to education, research, and technology as the key drivers of regional development. We believe that through knowledge and cooperation, we can create new opportunities and a better future for our communities. With thanks to UPTC and organizing committee for their leadership in making this international dialogue possible. May these days inspire new partnerships, ideas, and discoveries that benefit not only the scientific community, but also society as a whole. Welcome to Tunja and welcome to IQS 2025. Thank you very much.
Thank you, Dr. Haberman. Now we are going to have the words given by Hans Jessit Ramirez, who is the chairman of the International Symposium on Quantum Science and Engineering.
Good afternoon, dignitaries of the honor table, our appreciated international invited speakers, faculty, researchers, students from the different universities being part of this event, and all the public who are there. Thank you very much for being here. We really appreciate your contribution from one way or the other to this event. This is the first event of its class in the history of this city, and actually in the history of all this region of the country, the center and southeast of the country. We're very glad to have been able to gather scientists from different parts of the country, actually from different parts of the world, to talk about a very relevant topic. Now, I had a few slides for this part, and there was like a little difficulty arranging the times. So, okay, so one of the challenges is that we will need the dignitaries from the honor table to go to their chairs, to the seats, so that we can see the screen. So I need to move a little bit so to be able to see what is showing. Please put the first one. Excuse me? Yeah, this is okay. Okay, so we really would like to thank also to the different entities or offices that made this possible. From the UPTC, of course, there is the Vice Chancellor of Research and Outreach, the Centers of Research and Outreach from the College of Sciences and Engineering and the college itself. And also we appreciate the support from the National System of Royalties and the government of the department, our department here in Boyacá. And as the presenter said, we are in the framework of this International Year of Quantum Science and Technology. So it was over there in 1925, and Heisenberg brought a very important idea for the later development of quantum mechanics, and that is why the UNESCO has designed 2025 as the year to celebrate 100 years of the quantum mechanics as a formal theory. So this is an actual important topic, not just for scientists, for people who are concerned or interested in basic research. So could we see the next one, please? Yeah, there are just very few, so we can just go with discussions. So this is a breaking news from this week. In a serious journal, in a serious newspaper, and it says that the next big quantum computer has arrived. So we are not talking anymore about the speculation. Of course, we are in the development of a bunch of new technologies based on the quantum physics of isolated microsystems. But we are at the point, we are at the edge of start getting real technologies that are useful for something. It doesn't mean that the process is finished. Of course, more things are necessary to go on. But what we have here announced is a computer, quantum computer known as Helios. So could we go to the next one, please? Helios is a quantum computer for sale. This is this company, probably the biggest quantum company in the world, Continuum. Actually, we have one researcher from Continuum in our advisory committee. We are very thankful to our advisory committee. And then they just announced that they are selling this computer for companies, for industry. This is not a prototype anymore. So could we go to the next, please? So what they announced, we assume it is true, is that they work with 98 physical qubits. So as Professor Ulloa said this morning, qubit is a basic unit for working with information at the quantum level, and then increasing the number of qubits is critical to be able to manage challenging tasks. So 98 physical qubits is a good number. It's not the highest number that quantum processors have shown so far. But what is impressive in this product, let's call it that way, is that they announced 48 logical qubits. So 1 year ago, at least tens of physical qubits were necessary to have one logical qubit. Now we are talking that more than half of the physical qubits are logical qubits. So it means that this computer, based on 48 logical qubits, is able to deal with problems that classical computers definitely are not able to process. So there's one more information there. So the biggest supercomputer that actually there is, the biggest actual supercomputer existing on Earth is El Capitan there in California in the USA. The speed of that computer is 10 to the 15 flops. It means per second it can carry out operations at that level. This is a very, very big number. But then with this Helios computer, because they have 48 logical qubits, they can process information at the level of 10 to the 48 data per second, let's say, per run, talking about super dense encoding. So we are really talking about something that is, again, a quantum advantage without any doubt, and that is for sale in the market. So this is just one motivation to say that we consider that to talk about this kind of technologies is very important, not just at the level of basic science. Of course, we are organizing this event mainly from the School of Physics, mainly from colleges of science, but we intentionally call this event Symposium on Quantum Science and Engineering, because we are at the point that we really need to sit down to have conversations with people who are able to work at a much more applied level, because now we have some technology to face interesting problems. So, just having said that, let's go to the next one, please. I am about to finish. We really hope you have a great time here in Tunja. For the ones who are not from here, welcome to the UPTC, welcome to Tunja, and welcome to Colombia for the ones who are not from the country. We are so glad of having you here. We hope for the next 5 days we learn a lot about quantum science and engineering. We increase in motivation, we increase in enthusiasm with researchers, colleagues, and students, and then we hope you collect great memories of your time here in Tunja. May the Lord Jesus Christ bless you all.
Thank you so much. Now we have the words by the director of the physics program, Hernán Olaya Dávila.
Buenas tardes a todos. I'm Hernán Olaya, Director of the School of Physics in this university. And sorry, it's been about 1 year since I last spoke any word in English. But let's start. Good afternoon, everyone. Welcome to the International Symposium on Quantum Science Engineering, IQSE 2025, organized with the Pedagogical and Technological University of Colombia throughout the Quantum Computing and Information Theory Research Group and his leader, Professor Hans Ramirez. Today is an honor and a pleasure to have the attendance and participation of this important group of national and international researchers who have come to our university and to share their work and expertise in the field of quantum science and engineering. We live in an era in which the limits it was possible being redefined. The laws on quantum physics we just a century ago seemed like an abstract theory, a reserve-only theory, and now driving a new technological revolution. From the study of subatomic phenomena to the development of quantum computers capable of performing calculations we previously considered impossible, the quantum world invites us to rethink reality, information, and knowledge. The importance of quantum science and quantum computing lies in the fact that both represent a scientific and technological revolution with the potential to profoundly transform how we understand and apply information, energy, and matter. in this academic space during these days. Plenary sessions, discussions, and conferences will be held in these academic spaces. The School of Physics wishes everyone to pleasant stay at the city in Tunja, and hopes they take advantage of the event to learn and further understand the nature of quantum phenomena and their impact on the present and the future technology. And welcome again. Thank you very much.
Words by the Director of Research, Dr. Yolanda Torres Perez.
Good afternoon to everyone. Good afternoon. Yes. Welcome to UPTC. I don't write my words in English, so I am very apologize. But I am going to speak with you in Spanish. Sorry. Bienvenidos a todos y todas a la UPTC. Un cordial saludo también a los que nos están escuchando por Edumedios, que se está transmitiendo. Para nosotros es un placer darles la bienvenida a este primer International Symposium on Quantum Science and Engineering 2025, que esperamos que sea no el primero, sino muchos los que tengamos de estos simposios en donde tenemos tan importante tema de discusión, como lo dijo el profesor Hans. El tema de la mecánica cuántica y la física cuántica es un tema que, como lo acaba de mencionar, tiene dimensiones muy, muy fuera de lo que en este momento estamos concibiendo. El mundo avanza con gran velocidad y sin precedentes, porque vemos que la física, la ciencia avanza con gran velocidad y estamos llamados precisamente a mirar cómo nuestro conocimiento se acerca a esa frontera. Por eso tan importante la participación de nuestros conferencistas internacionales, en donde van a compartir con nuestros estudiantes y docentes todos sus conocimientos. Un especial agradecimiento a nuestros invitados internacionales por aceptar la invitación que les hizo el profe Hans de estar aquí en la UPTC, su casa, a nuestros conferencistas de Canadá, Estados Unidos, Alemania, Francia, China, Taiwán y Singapur, así como nuestros colegas también de los Andes, la Universidad Nacional, y obviamente nuestros docentes aquí de la UPTC. A todos ustedes, mil gracias por su presencia, por su entusiasmo, y esperamos que estos 5 días que van a tener acá analizando estos avances de la física cuántica, la ingeniería cuántica, sean, como lo dijo el profe Hans, un estímulo para hacer proyectos de investigación, para hacer movilidades académicas, para mover esa frontera del conocimiento acá desde territorio. No siempre debemos pensar que la frontera del conocimiento se mueve en otros países, sino que aquí también podemos hacerlo. Los invito a que aprovechen y disfruten todos estos días al máximo de este interesante simposio y recuerden que la casa de ustedes es la UPTC. Muchas gracias.
Thank you so much. So in this way, we open the International Symposium on Quantum Science and Engineering, IQSE 2025. And now allow me to introduce you Professor Dr. Paweł Haberlak, who is our keynote speaker. He is a physicist from Rockland University of Technology, Poland, PhD from University of Kentucky, USA, full professor of physics from 2014 at University of Ottawa, Canada. Before that, he was principal investigator at National Research Council of Canada. He has been visiting or adjunct professor at Brown University of Colorado at Colorado Springs and Tohoku University in Sendai, Japan. He has been distinguished as honorary professor at Wrocław University of Technology, Poland, fellow of the American Physical Society, and fellow of the Royal Society of Canada. He has been awarded the title Professor Titular of Physical Science by the President of Poland, the Outstanding Research Achievement Award for the Development of Single-Spin Transistor, the Brockhaus Medal of Outstanding Contribution to Condensed Matter Physics, the Humble Research Prize, the Humble Foundation, Germany, and the Queen Elizabeth Diamond Jubilee Medal of Contribution to Canadian Science. So in this way, welcome Dr. Powell Rockland.
So, would you prefer to be there or here?
I will run here.
Okay.
I don't think I need it. Can you hear me in the back? Yeah, I think, okay, because I am using the microphone, but I don't want to use
Just in
the
case, we will be.
I will be talking about, yes, sorry. It's difficult to run with the microphone here.
There are some people in the YouTube channel looking.
Okay, they could move forward. Okay, so I will be talking about synthetic topological quantum matter and how we try to make it with quantum dots, so controlling matter at the atomic scale. So our goal is, as I said, to create synthetic topological quantum matter, and this way realize macroscopic quantum states in semiconductors. Yes, so Hans was showing computers. They are mentioned about computers which are all based on superconductors. But we have $300 to $600 billion semiconductor industry what will happen to this industry if all our computers run on aluminum. So perhaps we should try to implement, and why superconducting computers are so good, because they operate on the basis of macroscopic superconducting quantum states, yes? So if we could realize macroscopic quantum states in semiconductors, then we could address many challenges that are still in front of us. And we will be doing this by designing matter and devices at the nanoscale. Right, so I will cover some of the activities in our group. We work on quantum circuits based on electron spin, so we are building quantum processors based on individual electrons that are positioned and operated in field effect transistors. We are working on quantum dots that are sources of single and entangled photon pairs on spin-photon interface as building blocks of future quantum internet. We are working on something that is used today on quantum dots in self-assembled quantum dots, as gain medium in quantum dot lasers. So this is something you can buy now, yes, that improves significantly semiconductor lasers, which are everywhere. We are working on nuclear spintronics. So solids or atoms that solids are built of have also nuclear spin. And if we could access this nuclear spin, that would be a very nice resource. So it is not easy to control this nuclear spin, and with electron spins, which is what we would like. And so this, there is a significant theory behind it. We are also working on quantum dots in topological insulators, which have topologically protected surface states. These structures are expensive to make. They all require molecular beam epitaxy. And we are also working on printable semiconductor structures, so nanocrystals. We have recently demonstrated a lasing from nanocrystals, working with Ted Sargent. We work on graphene and graphene-based carbononics, so combining electronics, photonics, and spintronics in a single material system. And we are working on 2D semiconductors, such as transition metal dechalcogenides, as molybdenum and disulfide shown here. So I will show some examples of what we are doing and where the challenges are and how we are overcoming them. So the outline of my talk is I will discuss some of the computational tools we have developed. Then I will talk about topology and topological insulator quantum dots. Then I will focus a little bit on quantum wires, quantum dots in quantum wires, which are grown at the National Research Council of Canada, and discuss the single and entangled photons emitted from these structures. Then I will move to topological quantum matter in Haldane quasiparticles and talk about Majorana fermions. And then if time permits, I will talk about graphene-based electronics as carbononics and discuss in some detail broken symmetry valley and spin states in voltage tunable semiconductors in bilayer graphene. I think I have to move here. Okay, so let's briefly describe computational tools that allow us to move forward. So we have developed a computational platform for million atom nanostructures called QNano, where we start from atomic composition. So this is indium arsenide quantum dots, graphene quantum dot, nanocrystal. We determine shape and composition for something of the order of 1 billion of atoms. Then we calculate atomistic strain for, again, about 1 billion of atoms. We use these atomistic strain calculations for and ab initio output to determine effective Hamiltonians. And we use different effective Hamiltonians, mainly the atomistic tight binding sp3d5 model, and that gives us electronic states for the order of 1 million atoms. Then we move to computing Coulomb matrix elements, which is a significant roadblock here, and then use various configuration interaction inspired, DFT inspired tools to predict multi-exciton generation, high excitation optics, high bias transport. So let me show how this works for this topological insulator quantum dots. So topology is something that has a long history. One of the first papers discussing topology in intersection of potential energy surface and polyatomic molecules is by Gerhard Herzberg, president of the National Research Council of Canada at the time. And according to Frank Wilczek, this was the first mention of Z2 invariant and generation of Herzberg circuit. This concept of topology was later followed by Mike Berry in his famous paper on quantum phase factors accompanying adiabatic change. So we have been building on these contributions, and let me discuss the consequences of the topology on the basis on the mercury telluride quantum well. So mercury telluride has a topological to normal insulator transition as a function of thickness. For narrow layers of mercury telluride quantum well, it's a normal semiconductor. But for thicker layers, it becomes topologically non-trivial. And we will describe this in greater detail using K.P theory for Latinger spinors. So the first simplified version of this theory is the Jean-Bernevik Hamiltonian. So it's a 2x2 Hamiltonian matrix describing electron decomposed into S states and B states. So S states A, B states, heavy hole states. And the problem is solving the contribution of these different types of states to the wave function of the electron. So if we look at this Hamiltonian can be written as a vector D dot sigma, where sigma is the vector of Pauli matrices. And this vector D depends on these parameters of the Jean-Bernevik Hamiltonian. So it's a function of wave vectors, Kx and Ky. So this vector D, through this vector D, the Hamiltonian depends on parameters K. So there is, in the Hamiltonian, there is a mapping of K-plane into a Bloch sphere. And so this is the result of this mapping. If we look at the vector D, the normalized vector D, so D over the norm of D, and for normal bands, we see that this vector covers, as a function of wave vectors K, covers half of the Bloch sphere. So this blue here is when D is equal 1, the amplitude of it. So you see that for inverted bands, this vector D covers the entire Bloch sphere. Yes? So now the difference between the two is that there is one hole for normal bands and 0 holes for inverted bands. So through this geometry, you see the consequences of non-trivial versus trivial topology. This way you can visualize this. Sorry. So now, is it really true? So let's look at the computation of this topological to normal insulator transition as a function of thickness. Remember, narrow, normal, thicker, topological. Somewhere there is a function transition from normal to topological as a function of thickness. So we are doing discussing results of the K.P calculations of 8-band Latinger spinors. So this is a result for a quantum well, so infinite in the plane quantum well, and you see for narrow quantum well, we have lower energy states are P-like, and higher energy states are S-like. And as the thickness increases, we have a transition from ground state from P to S. So here is normal bands from P to S, and then here is from S to P transition, and there is a particular thickness for which there is a crossing of the two bands. And now when we look at this particular critical thickness, we have a linear in-plane dispersion, so our excitations are Dirac fermions, single Dirac fermions. In graphene, there are two Dirac fermions that cancel each other. So this is now for a quantum dot. So now we have a quantum dot with the height of 3 nanometers and some fixed diameter of, I don't remember how many. And when we have the finite radius, we have energy levels as a function of angular momentum. So we see energy levels, and there is a gap, no states in this gap, and energy levels in the conduction band. If we make a thicker quantum dot, we see that in this gap we have other energy levels, red and blue. And if we look at these energy levels in the gap, for example, this one, we see that they correspond to electron spin down localized at the edge of the structure, at the boundary with vacuum, and a heavy hole, also localized heavy hole with particular spin -3/2. So we have edge states that are in the energy gap of our quantum structure. Now it turns out that one can tune this band inversion with strain. And so now this is tuning band inversion with strain. We see that if we start with no strain and states in the gap and apply strain, this opens the gap and there are no edge states with only 2% of strain. So now you can imagine that the presence or absence of the edge states will control the conductivity through such a quantum dot. So we imagine we have our quantum dot, we attach source and drain, and now if there is this edge state in a quantum dot, a current will flow through the quantum dot, high current will flow. If we, on the other hand, go to the transition to the normal state, then there will be no current flowing because there will be no edge state. So this way, you can imagine detecting strain-driven transition and detect strain at the nanoscale, because this transition from normal to topological state of this quantum dot is very sharp as a function of applied strain. So you have almost an immediate application of this effect of topology on our quantum dots in topological insulators. Now let me move to quantum dots in nanowires for single and entangled photon sources. So this describes schematically a growth of indium arsenide phosphide quantum dots in indium phosphide nanowires. You know, indium phosphide is a very important material, semiconductor for ICT, because this is a material which has a band gap matching the channel in silicon fibers. So all the current information transfer through fibers goes at the energy of the band gap of indium phosphide. So now we will be doing quantum dots in indium phosphide nanowires, and we start with an indium phosphide substrate covered by PMMA. Then we lithographically define an opening in PMMA and deposit a particle of gold. And then we turn on deposition of indium phosphide, and this indium phosphide runs into this gold nanoparticle and starts building up, growing a nanowire. So when you stop, you see a nanowire grown with a gold particle at the top. And if we stop this growth at some point and start depositing indium phosphide, you will create an indium phosphide quantum dot in this nanowire. You can also clad this nanowire with indium phosphide and protect this quantum dot from interaction with environment. All these pictures are from Dan Dalaku and Philip Poole, my colleagues at NRC. So now we use lithography, VLSS, and CBE growth of these nanowires and quantum dots. This indium phosphide quantum dot, we know the position, we know shape, we know diameter, we know height, and we know average concentration. What we don't know is the actual profile of arsenic in indium phosphide. And there are other problems. For example, the structure has about 1 million atoms. So this is one more time. This is a quantum dot that has a concentration of arsenic versus phosphine in it. And we describe this quantum dot by one electron Hamiltonian, which describes electrons on indium, on arsenic, on phosphine, spin-orbit coupling, and tunneling between different atoms. We then describe excitation of this quantum dot by multi-electron hole interaction Hamiltonian. So here we have electron-electron interaction, hole interaction, and direct and exchange electron-hole interaction in this quantum dot, and all of this is handled through a Q nanocode. So if we look at this quantum dot, the nanowire itself has a hexagonal structure. So it is an indium arsenide phosphine structure with about 20% of arsenic that replaced phosphine. So if we actually look at this atomistic structure of a quantum dot, then from the top you see random distribution, about 1/5 of atoms are replaced. Yes, and there is some random distribution of these arsenic atoms, and the same is cross section on a side. You see also random distribution of atoms, which roughly describe the quantum dot. So nevertheless, despite this disorder, there is a shell structure in the conduction band. So here is a calculated ground state, electron ground state, 2 excited p states of the quantum dot, d states, and so on. So an important an important thing to notice is that despite disorder in individual quantum dots, they all preserve the shell structure in the conduction band. In the valence band, it's a little more complicated. Yes, so here you see a TEM picture of a quantum dot in the indium phosphide nanowire, typically some thickness of the order of 3 to 5 to 6 nanometers, the diameter of about 20 to 40 nanometers. And you can grow thicker and thicker quantum dots, and different quantum dots with different thickness emit at different energy of light. So that one can control the emission energy from such a quantum dot by controlling the thickness. So now what we need to understand is we measure the recombination spectrum. So these dots are photoexcited, and electrons and holes recombine and emit photons, and one measures these photons. So there's an energy of the photon and intensity of photons. And one would like to, this is the low energy spectrum, one would like to understand what are these emission peaks telling us about the structure. And we can do this by computing. So here is a result of, for assumed distribution of arsenic atoms, here is a result of creating such a quantum dot and then calculating using Q nano, which I described, an exciton, positively charged exciton, bi-exciton, and trion. Typically, configurations for such structure involve about million configurations, million to several million configurations. So when we calculate this, what we can say is that the highest energy in these complexes is exciton, then X plus, then XX, then X minus. And if we look at our experimental results, we see indeed that we see an exciton, that's this structure. There is no positively charged exciton. There is a biexciton, which you can tell from intensity dependence of this peak, and then there is a negatively charged exciton. So you can measure and identify the spectrum based on computed multi-exciton spectrum. Now this is experimentally, when we are developing technology and step toward engineering, yes? So you want to, reproducibility is very important, and if not, then you have to defeat it. So what this is a picture of dot A, nominally identical dot A, dot B, dot C. Actually, about 40 dots were measured from identical runs, but they are a little different. So here is dot A, you see exciton and trion, and then intensity increases, so you are depositing more and more energy, exciting more and more quantum dots. You see a beginning of a biexciton, yes, biexciton, exciton, and then higher energy emission from the P shell starts appearing, yes, and you see that this dot is a little different than this dot, is a little different than this dot. The same can be said about these dots, yes? So nominally one needs identical dots, but they are never identical, so one puts gates near these dots and applies electric field and tries to control different dots to produce the same emission spectrum. Now, one thing that one would like to accomplish is to generate quantum dots in which the biexciton does not bind. So the biexciton energy is twice the exciton energy. So here is an emission from a biexciton in red. It's an emission from a trion. Difference between exciton and biexciton emission. And now you see that there are dots that emit with positive energy, where two excitons are binding, versus negative energies, where the two excitons are repelling each other. And what is exciting is that there are those dots for which there is no binding or repulsion between excitons. And for such dots, with vanishing of biexciton binding energy, one can generate, emit photon pairs which can be entangled. And the entanglement is a time bin entanglement. Anyway, by designing these structures, one could produce source of entangled photon pairs, as needed, for example, for quantum key distribution. So we try to understand how this can happen, and this is a quantum dot with a gradient of arsenic contribution. As you see, there is a little more arsenic than here. Yes? And if you compute this, the exciton and biexciton spectrum, you see that indeed there is almost a degeneracy between biexciton and exciton. So there is vanishing of biexciton binding energy. And so these are dots that are being developed for future quantum internet. Okay. How am I doing with time?
You're fine. You have almost 15 minutes.
15 minutes, okay. So now we will use these quantum dots in nanowires to build topological quantum matter. So we will do this by building synthetic spin-1 chain, which is synthetic spin-1 chain is a paradigm for topological quantum matter. It is a macroscopic quantum state in our semiconductor nanowire. So this is one of our goals. How do we do this? I described the construction of this quantum dot in a single nanowire, but imagine that we will grow an array of these nanowires, of these quantum dots in a nanowire, and now in each quantum dot we will put 4 electrons. These 4 electrons, 2 of them go into S shell, I described this S shell, and 2 of them go into P shell. exchange interaction between these electrons will align their spins. So in this, for 4 electrons in this quantum dot, the ground state is a spin 1 object. Now we are growing 2 of those 2 quantum dots close to each other, and we are looking at the formation of a p-shell of a double quantum dot. And if you look closely, you will see the characteristic probability density of a double quantum dot. So we put in each quantum dot 4 electrons, so total of 8 electrons, and we calculate the ground state of this electronic complex. So this is a very large system. I think with this basis, it was about 2 million states. And we look at the low energy state. And low energy state, you see single state, so a singlet for these 8 electrons. You see a triplet, S equal 1, and you see a quintuplet, S equal 2. Yes, so we can think about the ground state of these 2 coupled quantum dots. It's here. As effectively described by a Heisenberg Hamiltonian of 2 spins S1 and S2, each one spin 1, coupled through exchange interaction J. Yes, so very complex system for particular set of parameters. It can be thought of as a manifestation of the Heisenberg Hamiltonian, Heisenberg couple system through this number of states, so singlet, triplet, and quintuplet. So now we just replace every electronic complex in the quantum dot by a spin 1 and generate Heisenberg Hamiltonian and diagonalize this Hamiltonian. And we see now the energy spectrum as a function of number of quantum dots. You see singlet with S equals 0, so the blue line are singlets for different number of quantum dots with 4 electrons each. You see triplet in this low energy spectrum, and then you see a quintuplet, which I think is quintuplet here. Yes? So you see a fourfold degenerate ground state separated from a large number of excited states by what is called a Haldane gap. So this shows here the expectation value of spin on a given site of our array. Yes? And we look at the edge of this structure, and we see we have spin 1 objects, but the spin at the edge is 1/2. Yes? So this means that spin at the edge is 1/2. We have 2 spins 1/2, so that's 4 states. Yes, that's why we have a fourfold degenerate ground state and protected by the gap from the quintuplet, from this red line. So we see fractional spin quasi-particles at the edge of our spin 1 chain. You can imagine that you have a 1 meter long chain, completely macroscopic, and yet at the edges of this chain there will be quasi-particles, fractionalized quasi-particles that generate effectively four states equivalent to 2 spin 1/2 Haldane quasi-particles. So this is illustrated here. We pair these, we divide our spin 1 states into spins 1/2, and we have now 1 spin 1/2 at the edge. Yes, remember it is a spin 1 object, but fictitious spin 1/2s. They have this fictitious spin 1/2 here. We have this fictitious spin 1/2 here, and all other spin 1/2s are paired. So we have edge excitation because it's a topologically non-trivial system. It has edge excitations, which are Haldane quasi-particles. Now, if you think about everything else but these fractional Haldane quasi-particles, then you can create macroscopic singlet triplet qubit that corresponds to these Haldane quasi-particles, spin up, spin down, plus, spin up, spin down, spin up, minus, up and down. So right? So you can take these topologically protected quasi-particles and you can build an effective spin qubit in a macroscopic object. I think I have 5 more minutes. 10. Never happened. Okay, so we are working with these nanowires because my colleagues can grow the best in the world nanowires, and really fantastic. And we are trying to realize Majorana fermions with these semiconductor nanowires. I think for Italians it would be Majorana, not Majorana, but correct me. So we are using this indium phosphide quantum dots in indium arsenic phosphide quantum dots in indium phosphide nanowires to build a Kitaev chain and to demonstrate Majorana quasiparticles. And with these Majorana quasiparticles, the next step is demonstration of braiding of these topologically protected qubits and decoherence-free quantum computer. But that's a long way. So what are we doing now? We have our array of quantum dots. So this is a potential seen by electron in the conduction band. Yes, when you have a quantum dot, I have a lower energy state, and I have a barrier, low energy state, and so on. And now we are combining it with a superconductor, perhaps iron selenide, ferromagnet, perhaps chromium iodide 3. We will try different materials. And this wire is described by a Kitaev Hamiltonian. So I have tunneling of electrons from different dots to different dots. I have a pairing, so if they are next to each other, there is a pairing energy. They form Cooper pairs, yes, and they are in contact with superconductor, so there's a finite chemical potential, and this particle number fluctuates. So there is tunneling, there is superconducting pairing, and there is fluctuation of electron numbers. So let me try to explain what such a simple system really does, really represents. What we will do is we have these fermions on each side. So on each side, these lost indices, but on each side A, we have fermions C and C+, and we break this quantum dot fermion C into a pair of Majorana fermions gamma. So on each side, we rotate the fermion operators into Majorana operators gamma on the same site. So these are this is the transition from fermion operators on site J to Majorana operators on the same site J for C and C+. Then when we convert our Hamiltonian from normal fermions to Majorana fermions, now the discussion will be limited only to a particular case. We obtain a Hamiltonian which involves Majorana fermions. But this Hamiltonian shows that Majorana fermions are not quasiparticles of a Kitaev chain, because the Hamiltonian is not diagonal in Majorana quasiparticles. It involves Majorana quasiparticle on side J and on side J+1. Yes, so this is not diagonal in Majorana fermions, so they are not quasiparticles of a Kitaev chain, even though most literature refers to that. So one more time, we have a Hamiltonian that is non-diagonal in Majorana fermions, and what we do to diagonalize this Hamiltonian is to pair Majorana fermions on neighboring dots and create bond fermions AA+. So we have 3 types of fermions: normal fermions C, Majorana fermions gamma, and bond fermions A. It's a little crowded. But so we make a transition. These bond fermions are bond fermions because they involve a particle, Majorana particle on side J and on side J+1. Yeah? So they involve Majoranas on 2 different sides. That's why bond forms between different sides. Yes? So we have the A and A+, and now And now we effectively, these arrows here correspond now to Majorana fermions. So for each quantum dot, I have two Majorana fermions. The arrow down or arrow up, these are the Majorana fermions 1 and 2. And now I am pairing, forming bond fermions. So pairing from one dot, dot 1 to dot 2, the two different Majoranas, yes, two different Majoranas, gamma 1 and gamma 2. Yes, on different sides, as I said, it's crowded. And then I do this pairing to forming bond fermions A, and I am left with dangling Majorana operators of two different types at the beginning and end. Yes? So here is a dangling Majorana spin down here in this picture, dangling Majorana spin up in this picture. Now when we convert our Hamiltonian into bond fermions, then we see that these bond fermions diagonalize the Hamiltonian. Yes? The Hamiltonian is in a diagonal form. Right? So we can construct exact eigenstates of this Hamiltonian, but we see one has to be very careful because we are summing over over n minus 1 bonds. When you have n sides, you have n minus 1 bonds. Yes? Only for n minus 1 bonds. And so we see that one bond is missing, mysteriously. Yes? So Hamiltonian does not include a non-local fermion which will be created from Majorana fermion at the end of the chain, site n, and Majorana fermion at the beginning of chain, site 1. So we call this bond fermion capital N, yes? It's from this bond fermion site, or from this bond, it goes to the beginning, to the first one. So this bond fermion is built with H Majoranas, gamma 1, 2, and gamma n 1. Okay? So now let's repeat this picture as we did for Haldane quasi-particles. We have our diagonal Hamiltonian. It involves n minus 1 bonds. Now these arrows are Majorana fermions, and the circles here are bonds between different sites, different sites. And we have these bond fermions, these Majorana fermions dangling at the beginning, at the end. And now we are forming this bond fermion N that entangles the first Majorana and last Majorana. Okay, so you have an object that entangles the two Majoranas at the ends of the. So they are talking. I'm sure it's less than that. So we form this bond fermion out of dangling Majorana fermions. And to complete our Hamiltonian, we need to add this edge bond fermion into our Hamiltonian. We can only do it with 0. So this way, because this Hamiltonian is diagonal, we know what the energy of each fermion is. So for a given number of bond fermions, we can assign the energy. And this way we know that for these bond fermions, we have to assign 0 energy. So this is how a 0 Majorana mode really appears as a bond fermion, non-local, involves entangled pairs from the beginning and end. Yes, the beginning knows what the end is doing, and they are at 0 energy. So non-local bond fermion with 0 energy entangles Majoranas at the two ends, and this leads to the degeneracy of ground state and potential for braining. Okay, we can probe these bond fermions and Majorana particles using light. So light comes in, is absorbed, photon is absorbed, exciton is created, and these excitons interact with Majorana quasi-particles, and we call it Majorana exciton. So we can learn something about these Majoranas and bond fermions versus Majoranas with light. And we are also working on designing this Kitaev chain on a quantum computer using variational quantum eigenvalue solver. And I will only I will only, there were a lot of things, but I am going to the end. This is fine. Last slide. Last slide is cannot be omitted. Right. So I will stop here. I thank you for your attention, and most of all, I thank all my colleagues and collaborators who contributed to this work. So thank you.
Thank you, Professor Harlach, for your very impressive talk about these new results. So we kind of lose the chance to have some questions, and then just raise your hand, please, for questions that you may have about the presentation from Professor Harlach. Okay, Stefan.
So the Heisenberg Hamiltonian is clear. We are really doing microscopic electronic calculations using Hubbard-Kanamori model for this system and matrix product. In reality, maybe that's clear. The start of something that has SU2 has SU2, but in reality, if you're allowing me a second question, you have this exchange coupling, which couples these two dots. They must be very small, I would assume. And that's probably the energy scale experimentally. Can you comment? Yes, we have an estimate of this exchange coupling. It's related, exchange coupling is related to 2T squared over U, certainly proportional to gamma proportional to U. So you can estimate this rather quickly.
We have time.
It depends on the size of the dots, on the concentration of indium versus phosphorus. So the Q nano is giving us atomistic insight into this energy scale. So in fact, the hope was that this is rather large. That was original hope. It depends what's large for you, but certainly much larger than millikelvin temperatures.
More questions?
I am here tomorrow.
Actually, I
Yes.
would like to ask one question.
Yes.
What type of computational power do you require to do these calculations? What kind of computers do you use?
We have our own computers, clusters use about 240 CPUs, and then we go to Compute Canada clusters, which are of the order of 60,000 CPUs.
60,000?
60,000. We never use the 60,000, but if necessary, it's possible to go there.
So, but in some cases, you need more than 200.
In some cases, we need more than 200, but usually we first test the scaling of the program on our Zeus cluster.
One question over there. Sorry. Okay, one here and one there.
Let's
start with this one.
Okay.
Thanks. I just want to ask you about that implementation which we know that topological qubits are able to minimize the error in several stages. the implementation, you show using the spin qubits to create the topological one. How how the error is corrected with that implementation you use, or what is the enhancing error correction via the production of those spins?
So correction of errors. For Haldane, so when you have a topological system and there is a boundary with non-trivial, then you have some states, yes, which are quasi-particles of your non-trivial structure. So they are protected from different scattering. So if we look at this Mercury Telluride quantum dot, the edge states are protected from scattering that does not change spin. Yes? So if you have spin conserving, this cannot happen. You need to flip the spin and scatter back. So there is protection there. When we say topological protection for the Haldane chain, what this means is that the topology here gives you protects the low energy states of your spin chain. That is, I have the same structure of levels, not the numbers, but the structure of levels for, I don't know, 10 sites, 10 spin ones versus 12 spin ones versus 14 spin ones. Yes? So I can build my chain to the macroscopic limit because topology protects the structure of this electronic stage. Each time I will have one singlet, 3 triplets separated by a quintuplet. Yes, and this Haldane gap will be maybe a little different, but every time I will generate this spectrum. So this allows me to robustly engineering macroscopic states. Just like for a superconductor, you change the size of the superconductor a little bit, but the energy of a Cooper pair is practically unaffected. It's there, first of all. It's there. Yes, thank you. There was some other hand.
So the question
What was
is, yes.
How can you set a specific state on every quantum dot at the nanogrod array?
You have to repeat this one more time because I am attached to the microphone.
Yeah, or if you want, you can take the microphone and then everyone will hear.
Getting up is enough.
Experimentally, how can you set a specific state on every quantum dot at the nanogrod array?
How can I set a specific state on quantum dot? I don't
The
understand.
nanogrod. How can you set that is set on, for example, up and down?
Experimentally, I don't think you don't need to set anything. You need to measure what you have there, yes? So you can take STM and measure, for example, individual spins.
So you don't need to have the same population state in each dot in the array?
You have, we had the figure there, which showed SZ expectation value on a given site, yes? So you calculate the states of the entire chain, yes? You have states of the entire chain, and then you calculate what is the expectation value of an operator for a given site. So I am asking, what is the spin on site 2? And I need to take my state over which I am calculating expectation value, yes, and evaluate the expectation value on a given site. So experimentally, you don't control the actual site. You have a state that's coherent over the entire structure. For example, there you show you 1/2 down, up, down. You can compute this. This is computed exactly as I described. Expectation value of spin on a given site. Yeah, I'm not sure if I answered your question, but we can talk later. Yes.
I have a question in the same way. How you can control or modulate the parameters of the Hamiltonian in the model with this experimental montage?
How can I control the parameters? Well, I need to. Yes, so hopping depends on the wire cross-section, on the concentration of indium versus phosphine, on the size of the quantum dot. This can all be engineered. And then I calculate within Kinana, I calculate what the hopping is. Yes, if I just have two dots, it's a splitting S and P shell. Each state splits into two, bonding and anti-bonding. So I can compute this and give back to experimentalists, and they will know, they will measure this splitting. And then they will know what was the height of the quantum dot or what was the diameter. Yeah.
A bit
Yes.
of a follow-up to that is,
Yes.
so how robust is the formation of the Majorana at the end to the homogeneity of the sample? Because I imagine that you have early tunneling and so on. Could it be a situation that you have a Majorana somewhere in the middle, in addition to the ones at the end?
The fact that they are at the ends is guaranteed by construction. That is the way we form the bond. The bond operators are really the physical quantities.
All the bonds are, you have homogeneity.
I assume that all the bonds are identical. That simplifies the results of calculation. But we can certainly separate the part of the Hamiltonian where everything is identical to the perturbation. And we have done several calculations with disorder of tunneling, for example, matrix elements, and it did not make a qualitative change. Yeah, pretty robust. Yeah, I just had to remind myself. Sorry. Yes.
Sorry, about the material that you mentioned that was topological non-trivial when
Mm-hmm.
the pigments increased.
Mm-hmm.
About it,
Mercury.
my mind would imagine that would be the contrary, right? That if you have a really, really not thick but clean material, it would be topological non-trivial. So can you tell me more about why it is non-trivial when you have a thick material?
The why question is answered by the energy spectrum of the quantum world as a function of thickness, where we see evolution of S and P like states, yes, and they crossed, and so at least in the calculation, I don't know how to calculate at zero. You have S levels, you have P levels, and at zero thickness, I am not sure what it means. Perhaps just one atomic thick. I don't know if K dot P theory can be seriously taken at the limit of single atomic thickness. So I wouldn't go very far in this analogy. Yeah? But that I think is everybody agrees. I mean, Lawrence Mollenkopf's group also has this transition. So I think that your choice of S and P orbitals in the atomic limit and order. Yes, and yeah.
So is this material in bulk
This material in bulk under strain, I think, is a topologically non-trivial material. But it's a little more complicated. The transition, different dimension, it's a little complicated. The transition. I am not going to until I think. It depends on the direction where you can find, and things are usually more complicated than we would like to think.
I have one more question. You were showing at the beginning of the presentation a picture of how the quantum dot was still in our world. And I was curious about how can you look a brain or any the source of the brain in order to to extract information about the system in a way that is not optical but more kind of electrical.
No, you have a quantum dot, for example, self-assembled quantum dots or nanocrystal. There are several groups which take nanocrystals and then put them between the source and drain. So they have a wire, you break the wire. This gives you a gap, an opening between the two wires. So this becomes source, this becomes drain, and an insulator, and you put a nanocrystal in between these two wires, one being the source, one being the drain. So I think people do this. I can give you some references.
Okay, let's say the last question.
Sorry, I didn't talk about the silicon. We also are working on silicon, but I didn't talk about the silicon. So I presume you are talking about the indium phosphide nanowires with indium arsenic phosphide quantum dots. Yes? And they grow preserving crystallographic direction. It's actually absolutely spectacular because when you put this gold nanoparticle, you have everything under control, but there's only one thing missing. And this missing is the random distribution of arsenic atoms in a quantum dot. When you stop depositing indium phosphide, when you are depositing indium phosphide, atoms diffuse to this gold particle on this nanowire. And we have we had, I think, I'm not sure if it's still operating, but scanning electron microscope in the CBE machine where you could watch in real time how these atoms climb this nanowire to this gold nanoparticle and deposit itself, and this nanowire growth. And the growth is perfect because it's stabilized by the surfaces of this nanowire. It's hexagonal with high index surfaces, which are make it energetically extremely stable. So you can grow a nanowire 1 micron height. You're welcome. Yes.
So let's thank again Professor Harlak. And we will have the pleasure of having one more lecture by Professor Harlak tomorrow as part of the Express School on Quantum Frontiers. So, because we are good on a schedule, we're going to have a picture from the group. I don't know if this will be okay, they prefer we in that way sit. Okay, so if professors invited the speakers could come to more a center region. Everyone, okay, because the photographer is going to be from here, so we could stand up. Just standing up here. According to the program, we have now a break, a coffee break. The snack will be given in the previous auditorium in Climaco. So some invitees from the honor table will be going to their respective duties now. Thank you very much for accompanying us. And then the rest of us will be back here at 4:40. Before that, to start 4:40, the next part of the session. Thank you.
you.